Okay, so you got both. Okay. You got like a whole OBS rocking over there?
I'm
I
live
I haven't
now.
really learned how to use that. I have it, but
Oh yeah,
it seems complicated.
it's dope. It's dope. It's not that bad. It's like baby steps, man. Baby steps. If you ever need help or whatever, hit me up. I can give you like the quick tutorial. It's not that bad.
Yeah, give me a tutorial someday.
Yeah.
All right. If you're ready to be ready, I'm ready.
Hmm.
All right, let's just do it. I'll hit the button.
Cool.
Boom. We are live. Are we live on your channel as well,
Yes,
Alan?
yes, sir.
All right, cool. I had some people in the chat. I don't see anyone in the view, but hopefully that'll catch up. All right, well, I guess welcome, Alan, also known as Space Audits, to the channel once again. Today, let's try something different, something we have not tried before, I think, which is that Alan is going to teach me how the ether vortex works, right?
Yeah.
Am I saying that right?
Yeah. So
Um,
so I'm gonna go over like a summation of the experiments of like where I'm coming from and show you like how I'm what I'm drawing, my conclusions based on more or less. And you can agree with them or not, totally cool. And we could discuss the intricacies of them. I know for sure you want to get to the single axis gyro stuff probably.
yeah,
Yeah.
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 The
So
main
we
thing,
can jump right into it. Yeah, let's go.
the to summarize, the main thing that triggered this whole thing is you were on with MC Toon on Jaren's debate channel, right?
Hmm.
And you guys were kind of, just reading off back and forth. And what I felt was lacking was we didn't have this opportunity to say, well, hold on, I don't understand that. Explain that part to me.
Yeah. Well, that's what the
And you had
cross.
this diagram. So
Yeah.
that's what we're doing here. You're going to explain how this works.
Yeah, absolutely. So, in regards to the debate, yeah, McToon had every opportunity to question me during the cross examination, but if you remember, he yielded his time, all 7 minutes of it.
Okay. All right. Yeah. Fair enough. So let me rephrase. I
But
wasn't there to ask questions.
yeah,
It was well, it was a debate, right?
so you would like clarification on it, and like which I'm happy to provide. But yeah, more or less, yeah. Anyway,
It was a
continue.
debate. This is not a debate. See, I'm not trying to ask questions in order to prove that you're wrong,
Yeah,
which is what he would have been doing.
right.
I want to ask questions in order to completely understand what it is you're trying to explain.
Cool. All right. So with that,
So
we can
let's
just
do
jump.
that.
We can just jump right into it. So let's see here. Let's see. So let's start with the single axis gyroscope stuff, right?
Okay. And you
That's
want to do
prob
some screen sharing?
yeah.
Okay. Yeah. Let me
Should be
make you
should
big.
should be good to go.
How do I make you big? Solo. Boom. I'm going to turn off my banner
Cool.
so you have the whole screen.
All right. Cool. So for those of you guys who aren't familiar with the single axis gyro, do you mind if I give like a rendition of what we're all talking
Go
about for
for
our
it.
audience? Like, okay, cool. So for those of you who aren't familiar with the single axis gyroscope situation and all that, the way that they say that the single axis gyro gets the best readings on the globe is that you have to have it axially aligned with the axis of rotation, right? It has to be parallel to that, right? So if you have a device like, say, for example, your cell phone on your desk, it's flat. If you wanted to align it, if you wanted to get a reading with Earth's rotation, you'd have to tilt it by 45 degrees, right? And that's kind of what this diagram is illustrating here. It's different orientations that the device would have to be if we live on a globe to be in alignment to get those best readings. How am I doing so far on the mainstream narrative of it?
Yep, that sounds right to me. I
Cool.
even have a very similar slide prepared myself. So awesome.
Awesome. Awesome. Yeah. And then so we got this guy. So I started looking into single axis gyroscope correction angles and whatnot, because that would be an excellent supplementary proof for the globe if this was true, if you would get symmetrical readings at this location. Oh, yeah. So that's the other part to this, right? So um, at the 45th latitude, right? Let's just say this is the 45th, right? So you would have to correct it by 45 degrees. And at around this latitude, they get a fringe reading of 7.5 degrees per hour, right? So when they take their initial reading, they get their 7.5.
No, it's not 7.5, but
Yeah, well, I can show you the data that guy posted for
it's
it's pretty close, but because
point
it
0.7. It's 0.7 times 15, whatever that is.
Yeah, whatever it is, it averages out to 15 degrees per hour when you flip the device and take the inverted reading. They just add it out and then flip it, or add it out and then average it out. Right. So that's that's what they're doing there with the single axis. So this is a single axis sag neck interferometer. So what it does here is it rotates, 360 degrees clockwise and counterclockwise when it takes its readings. And then the orientation of the device, you see, has it off-centered here. Off axis by 45 degrees. And this gentleman's location is in Toronto. So he's at about the 43rd parallel. So on the globe here, he's making that correction angle to be in alignment to get the best readings. And he was getting around, what was it, like 7 point something, like 7.5-ish. And then he published, or, he did the flip and then the averaging out and all that. And you can find all the data and all that stuff on his website. It's very, very cool. Yeah.
Let me ask, are you saying he was not getting the 15 degrees per hour that he's supposed to get?
No, he got it.
Okay.
Yeah.
Okay.
Yeah. But it comes in the form of two readings though. Like, I don't know if you knew that, because I didn't know that. I thought that it was a single reading of 15 degrees per hour. But anyway, they take the reading at 45 and then they invert it 180 and take another reading. I didn't know if you.
Yeah, they want to average out any bias.
Yep. Yeah, got you.
Yeah,
got you. So that's where we get the 15 degrees per hour, or 15 degrees per hour in regards to the gyro and what it detects or whatever, right? So.
Yep.
Okay, so moving forward, we have two other examples of single axis gyroscopes and their respective correction angles. So this is the GINGER project. It stands for Gyroscopes, Underground, and General Relativity, or something like that. It's some acronym. It's whatever. Anyway, these are their apparatuses, and they have them at their 45-degree angle corrections. And this one is located in Italy at the 43rd latitude. And then there's a station in Germany that's located at the 49th. So all around that similar area where it's like, is it a globe? Is it a plane? Because in the flat, this is where we'll get into the flat Earth side of the vortex, right? So on the flat Earth model, it would just be your standard Gleason projection, right? An azimuthal equidistant projection. So kind of conceptualize that and kind of think of it from a, I don't have a slide for this, I apologize, but just kind of think of it like, a 2D view, like you're looking at it as it's like, laid down like a pizza, right? Like a floating pizza in space, you guys, I'm sure you guys can conceptualize that, right?
Your words, not mine, but yeah.
It's just for the visual aid, bro. It's all good.
Yeah, sure.
I'm just fucking with you.
We don't have to get, uptight about it.
No. Yeah, I'm just messing. So,
yeah, you're fine.
Yeah. So just kind of conceptualize that. And then from the center of that, there's a ether vortex, there's a stemming out from that center point, right? And it's all encompassing the disk that we live on, right? And it rotates east to west, follows an east to west rotation. And that is what they're measuring. So if you're on a plane and you want to align your device to the thing that's rotating, if you're on a stationary plane, well, the sky's the thing that's rotating, right? So you're going to correct your device at the same situation, at the same latitudes. So in these same respective places on a plane, so far there's not in any distinguishing correction angles or readings that would facilitate like symmetrical readings on a globe and also the correction angles. Yeah, go ahead.
You lost me there.
Okay.
You just said two things that I don't understand.
Okay.
But what I want to focus on right now is why, if we're on a pizza world, why do we have to tilt the device at the same degree as your latitude? Why is that? See, on the globe, you have a diagram and you show why, because it's a globe. Why on flat?
Okay.
Can you?
So the sky above us is rotating. So if you kept your device aiming at the not rotating part of the thing, you wouldn't get the good reading. So if you tilt it up towards the sky, that's where you start to get your readings.
Are you saying that the sky is not directly above me?
Are you saying that if you were 45, if you were at the 45-degree latitude on a globe and you were at the 45-degree latitude on a plane, if you were aligning it to Polaris and that was your way of aligning it to ensure that you were correcting it to the axis of rotation with the Earth, how would you distinguish the difference between the two correction angles if they're the same for a single axis gyro in both places?
I have some slides that might help explain my question, if I could. You don't mind?
Yeah, Let me pull you back
All
up.
right. Let's see here. Let me just share my screen. I'll share that one, and then we'll bring this up. Okay. Okay, I have to put myself on. Bear with me. I am my own producer.
You should fire that guy.
Fire this producer. Okay. Yeah. Am I screen sharing? Are you guys seeing that? No. Looks like that's not working. Oh, here we go. This is what we want. Fire that producer. Dang. Okay. Here's a bicycle wheel. So to keep things non-controversial, it's a bicycle wheel. And it is rotating like the green arrow shows. So if we were to measure rotation using a gyroscope at the hub, we would get rotation parallel to, we would get an axis of rotation straight up and down, perpendicular to the plane of the wheel. And if we measure anywhere else on the wheel, we still get perpendicular rotation, like so. Anywhere on the wheel, the axis of rotation is the same, and the rate of rotation is the same. That's what happens on a bicycle wheel. So I think you're telling me, let's see here, you're telling me that on our flat Earth, we do not get the same axis of rotation everywhere on the wheel. We get different axes. Is that correct?
Yeah, that's my suspicion. That's why I think that there's not any single axis gyro readings in the South that are publicized and talked about.
Well, but do we agree that physics does this? That this is, if it's a single rotation that's uniform throughout, that we will measure it as uniform throughout. We do not have to tilt these little gyros in order to measure the rotation.
Okay.
Okay, so that's how a bicycle wheel works. So then what you would ask me is, why would it be different? Why wouldn't it just be the same on a sphere or flat? This is why it's different, because,
well, it would be the same on a sphere.
Right? On a sphere, everyone is measuring the same rotation. It's just they have rotated with respect to like the axis of rotation.
Well, before we could
do that here, we should get the same axis of rotation. So my conclusion is there must not be a single axis of rotation that is shared by the entire Earth. Is that right?
Yeah, I disagree. There's a all-encompassing ether wind, and where you're measuring relative to the latitude, you're further away from the source of it, and you're measuring the increased speed of that. That's what interferometry is picking up. That's what's causing the variance in the speed of light with interferometry. That's why that's what this effect is measuring.
I think you're screen sharing the Zoom right now.
Oh, apologies.
Which is okay. I mean, I tried to put you back on.
Oh no, you're good. You're good. You were talking, and then I was waiting.
So I think that's what I need explained. I've shown you my diagrams of how I explain what I expect.
Yeah.
Now you explain to me where that was incorrect and why.
So before we could even substantiate your diagrams, though, we would need readings at those latitudes to even verify that there are symmetrical readings all across the globe. As I showed you, I could only find instances in 3 areas, and they're all at the same latitude, roughly.
That's a separate point. I think it's a good point. You showed 3, and they're all in the northern latitudes. They all happen to match exactly their latitude.
For both models.
But it's 43 degrees and 49 degrees, right? So, I mean, like, whatever, right?
My point, exactly. So we're talking symmetrical readings on the globe, like in the southern hemi, right? So you're talking some people in Australia, some New Zealanders, maybe.
But isn't that enough for us to agree that that it's not the same everywhere on the surface.
Come again?
We can agree that at 43 degrees in, where was it? Somewhere in North America.
Mm-hmm.
And also at 43 degrees in Italy, they both measured the same rotation, right?
Oh yeah, that's not my point of contention. We're talking going further away from those spots.
I think this is enough. This is enough. We don't need to go to the southern hemisphere because they both tilted like so. They didn't tilt like that. They tilted like this. One's in Italy and one's in North America.
And do you think it would be do you think it would be different on a plane at 45 degrees when you're aligning it to the sky?
I think I think
if the center axis of rotation is at Polaris or something like that, then that's why the readings would be the strongest, because they do the same on the globe. Those Ginger projects, they say that they're aligning it with Polaris on the globe relative to where they're at. So it's literally the same exact thing as a plane at that latitude, right? So when you want to draw, go ahead.
I think that if you have a single axis of rotation, everywhere on that surface that is rotating measures the exact same rotation.
Agreed.
But you said, let's ignore this one. Let's just take one and imagine this is Italy. Imagine this is North America.
Mm-hmm.
Those are not the same axis of rotation.
So they're both tilted. They would both be tilted in the same way, bro. Like, I don't understand what,
do those look tilted in the same way to you?
Oh, that's your model of how you think that they would be tilted. Like, they both are 45-degree correction angles. That, like, you just tilted it on a different angle because it's on the other side.
Are they parallel?
Are they both aligned to the axis of rotation in the northern hemisphere relative to where they're at? Yes or no?
I'm sorry, say again?
Are they both aligned to the axis of rotation relative to the latitude where they're at? No, at the 45 degree, but only on the globe, though.
On a globe, they are.
Okay, that's fine.
Do you understand why?
I think you don't understand why they're the same, but continue.
Well, no, I don't. What I'm trying to say is that on a globe, they are those axes are parallel. They're literally parallel, right?
You assume that you're aligning it with a hypothetical axis that goes down the middle of the globe. I'm assuming that you're just aligning it with the sky. There's no difference between our two models at the latitudes that are provided.
The difference is in the globe model, we align them all to be parallel with each other. They're all one axis. But in the flat model, they are not parallel. There's one in Italy tilted 45 degrees towards Polaris. And there's one in Northern America tilted 45 degrees towards Polaris. How can this be the same axis? That's not parallel.
It's pointing to the same axis of rotation, my dude. Like you're just assuming that the axis is in the ground.
They rotate like this, that they don't rotate like this, right? They don't go this way. They go this way.
What?
They don't go like this. They go like this. So they're barreling around the surface?
No.
Like, okay, let me try a pen.
Uh-huh.
So here I am. I'm like in Italy. I'm pointing at Polaris.
Yeah.
This is the rotation.
Uh-huh.
So that cannot be that the sky is going around. That doesn't do this, right?
You're lifting the device off of the ground and aiming it towards the sky. If there's a vortex that goes down to the center goes down to the North Pole, right? Same thing. That's what they're aligning it to. As they get further away from it, I suspect that the readings get stronger and that they're not symmetrical for the globe. I suspect that it increases and that it's picking up a increase in speed in the ether wind.
Okay, when you say same thing, what do you mean?
The correction angles are identical. on a globe and on a plane at that latitude. There's no distinction
But
between the way you're aligning it with the hypothetical axis of rotation or the way that I'm aligning it with the hypothetical ether that's extending, an ether vortex that's extending down from the sky.
okay, why? I can explain to you why we align the way we do on a globe.
I just did.
They're all parallel,
Yeah, I just did the same thing to you.
but no, they're not parallel. You must agree. Hopefully you agree they're not parallel on a flat model.
They're aiming at the axis of rotation of the sky. This is the same position that they're orientated on the globe. Yes or no?
No.
You just showed me
Incorrect.
that they're 45 degree at the 45 latitude. If there's a ball in between my hands, this is at 45. This not the same? Continue.
Teacher, sir,
Go ahead.
I'm sorry, but you cannot aim at an axis. You can aim at a point, but you cannot aim at an axis.
My dude, axially aligned.
Okay, then that means parallel, not axial aligned. Alignment means parallelness. It does not mean
if the ground isn't rotating and you lift the device facing off of the ground, it's facing this, it's going to the sky. That's it. They're identical correction angles on the globe. I know it sucks.
It shouldn't be. That's what I'm struggling to understand. Why do you think, how do you justify that they are the same angle?
How are you not justifying that an all-encompassing rotation of the ether relative to the latitude wouldn't produce a varying speed the same way they say at the 45th latitude, you're spinning at 750 miles per hour. At the equator, you're spinning 1,000 miles. How do you not see the difference between the rotation of the ether and the mechanism of the turning of the globe being identical in that regard, especially when you're drawing your conclusion based off of correction angles at the 45th latitude?
I didn't follow all that. Can you say it back slower?
Yes. So how are you drawing your conclusion that you're aligning it with the globe if it's identical to lifting the device to correct or to aim it at the sky to get the reading of an all-encompassing ether that would produce the same effects that would be, you know how they say, hey, we're on the globe and you're at the 45th latitude, you're rotating at about 750 even though you can't feel it, blah, blah, blah.
Okay, let's pause there. No rattle on.
Sorry.
How do I justify that I'm aligning something in the globe model and I can't justify that same thing in the flat model? Is that what you're saying?
The correction angles would be identical, so I don't see why you're getting caught up on it. According to an ether model that you're trying to confine yourself to, though.
You must have a different model. If the model is, okay, let's say the Earth is still and the ether is spiraling around us. Okay, if the spiral is like we're sitting in a whirlpool, right? If there's a single axis of rotation, like a bicycle wheel, then everywhere on that surface is experiencing the same parallel rotations. So if they are not experiencing parallel rotations, then that means we are not in a swirling uniform.
If the Earth is stationary and there's a swirling thing over top of it, the stuff that's furthest out from the central axis of rotation is going to be going faster than the stuff that's closer. That's the variance. That's the variance in the readings. So your whole thing
doesn't explain the angle.
Okay.
We're talking about the angle right now, right?
It's axially aligned to the sky. You're confining the detection of the ether vortex, you know, blah, 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 to like however you need to so that you can't see it, like so that it doesn't make sense. Like I don't get how you don't understand that they're aligning it to the thing that's rotating. The sky
Let's just talk about the bicycle wheel.
Okay.
Let's not talk about anything that we're bound up in with our beliefs, right? Just a bicycle wheel.
Okay.
The axis of rotation is the axle that goes through the center of the wheel.
Yes. Are you placing the observer on the wheel or not? That's all we need to know.
No, let's just, we're holding the wheel. We'll just spin the wheel.
Cool.
The wheel rotates around an axis. The axis is a line, an infinite line that passes through the hub.
Okay. I think you're confused on the effects that are being measured here. Like, let's sidestep the
Well, hold
because
on. Before we do,
I think
I
this
want
will
to
help with the
understand
corrections.
this.
Okay, yeah, go ahead. Sorry.
What I'm stuck on is the words you're using.
Hmm.
So I want to get them better defined so we understand each other.
Hmm.
So an axis is a line. It's an infinite line. That is an axis.
Yes. For example, like the cosmic microwave background
So
would be
you
an
cannot
axis.
point towards a line. And if you align with, that means you are parallel to.
Hmm. And if the sky is above you and you're tilting your device up,
Now,
and
see,
the
as soon as you start the sky, you change the rules. When it's a bicycle wheel, we can understand that the axis is a vertical line going through the hub.
okay,
So anywhere in the world, another vertical line that is aligned to, here's my hub, here's my axis, here's another, this is aligned. This is not aligned. This is aligned.
all that would do then would just change the nature of the vortex from being connecting to the Earth. That's all that would remove, and it would just be that it's axially aligned with the, or with the sky. Then that's all that it would
So
change
the
in that regard.
so my understanding, and I think is what you're saying now, is that the vortex is not a simple whirlwind rotating around a single axis, but is instead twisted somehow so that
No, I just said it's not
it's got
connected
this
to the
axis
Earth.
here and this
I'll,
axis
I'll
here.
clarify. I just said it's not connected to the Earth in the way that I conceptualized it. You make a good point.
How is it connected to the Earth then?
Well, the way that I was conceptualizing it is that the vortex was stemming down to the Earth, and that there was a physical connection. But you make a good point about the alignment. That is a good point. So it would just be aligning it to the sky, then the thing that's actually rotating, without a connection to the axis. That would explain it. That would explain the not parallel exactly angles on the globe. The way
Well,
that you're
you just
talking.
said aligning again, and I'm so confused because to me, aligning means
Aligning in the
parallelism.
same way that you're doing it, just on a plane, dude. The same thing, just different axis, bro. You think that you're parallel to the axis of rotation. It's not.
Right?
Or I mean of the Earth, right? I think it's just aiming it towards the sky and it's getting the readings, because that's
But
all that gets
the
measured.
sky is everywhere, right? You're aiming towards a particular point in the sky.
Well, there isn't there the sky does intersect with the whole entire universe intersects with Earth's axial tilt, or the sun's ecliptic. So if we're talking about the rotation of the sky on that point, yeah, aiming it at the sky would probably produce a sidereal rotation effect, and that's what they all measure, which we can get
Okay,
into
so
later.
I think I heard that we aim at Polaris essentially. I mean, it's a couple degrees off, right? But where Polaris is the point that we aim at to get. Is that right?
Yeah, to be axially aligned with the Earth's rotation,
Oh,
or to tilt your device to the
with
sky.
rotation.
Either one, indistinguishable at the 45th Laddie.
Okay, and it is indistinguishable because not here. And this is what I'm really stuck on. It is indistinguishable not because we had a model that made this prediction, but instead because we made this measurement and we are now building a model that matches that prediction.
Mm-hmm.
Right? So in the globe version, we have a model that makes the prediction, but in the flat version, we are trying to build a model based on the observation.
Yeah, trying to piece it together. Yeah.
Okay.
I see how you're trying to frame it. Don't give a shit.
Yeah, no, you know what? I'm not trying to be controversial. I'm trying to come to an understanding, and I'm back to I think that the ether must have rotation that we measure that is tilted at different angles on different parts of the Earth, and that those axes do point towards what we call Polaris, right? The axis of rotation here and the axis of rotation here. And so the model that we're building is not just a swirl, but it's some kind of, I mean, Stephanie says it's a torus field.
I wouldn't describe the ether to the magnetic torus field movement. Like I wouldn't know how to map that. The way that I conceptualize it just based off of the readings and the effects is that it's a uniform field that's rotating with, sidereal time.
What do you mean by uniform?
So on the bike wheel, like the spoke is connected to the axis kind of thing. So like that, like it's just, all sweeping across like a big stream.
But I think we can agree that it's not like the bike wheel.
No, we can't because
it's not uniform. So we should drop that word.
What's that?
It's therefore not a uniform rotation. It's always 15 degrees per hour. So that's uniform.
That's yes. And the measurement that you get out of it, I'm sorry, you're okay. Let me rephrase. The measurement that you get out of it varies.
Right. So it's not
the ether is uniformly rotating. The measurement that you get out of that based on your latitude is going to produce a variance in the speed of light because that part's moving faster, right? If you're further away from the center.
Okay. So just to make sure I heard you right, I think you said the ether is rotating above us in a uniform way. And I interpret uniform to mean like a bicycle wheel.
Follow sidereal time.
How does sidereal time fit in to a uniform rotation?
That's all the measurements that they make. So you know how they say the globe rotates at 1,000 miles per hour roughly to produce its effects. That's a uniform rotation roughly. So that's kind of the idea. That's kind of the same exact thing. That it's just uniformly rotating. The effects they measure relative to the latitude is the variance in the speed.
Okay, and sidereal time, you mean like a sidereal day?
Mm-hmm.
Okay. Yeah, sure. Yeah, all right. That makes sense. Yeah. A sidereal day, not a solar day, is the rate that we measure of rotation. Yeah. Okay. I think that's probably as good as we're going to get. Is there anything further we can do about this?
No, that was good, man. You raised some interesting points. It's always good to rethink things on the back
again with the torus. Well, the torus. I don't know. That's kind of a torus, I think.
Oh yeah, this is just artist rendition, like visual eye candy. So like
maybe that can help us to understand what I'm talking about how it must be a different axis of rotation at different places. Let me make it big here. How do I make that big? There we go.
Can you see it?
Oh,
you're good.
Yeah. We're seeing it. You're good.
Well, let me put you over to the side here.
I'm not really sure what's going on in all this, but
yeah, this is just
kind of a donut-ish.
It's just conceptual art. The donut shape isn't related to the ether effects.
It looks like a magnetic. It looks like the magnetic field.
Yeah, can you hear me? Is my mic on?
Yeah, I hear you. You're still
good. Yeah. So the donut, like you can just disregard all that. This is just eye candy to show you, like, see how it's like transparently filled in a little bit, or like what's the word I'm looking for? A little opaque or whatever. It's like that's just to give you visual for like an ether encompassing the Earth and rotating with it. Like all these vectors and all that stuff is just visual stuff, right?
Yeah. There's a lot of visual noise in this. It's not exactly.
Yeah, it's not the best one, but my ability to do the Photoshop isn't great, so I just use my girl Patricia's. So.
Right, but I think maybe what this can help us visualize is the idea that it isn't just spinning around at 15 degrees per hour. It's got to be spinning like you can't see me.
Sorry, 1 second.
That's my fault. It's got to be spinning like this. Where like here's one side of the Earth, here's another side of the Earth, And that's the rotation that we're getting.
Oh, I got
So it
you.
can't,
One sec. Kind of like one
it's
sec.
got to be some kind of very bizarre sort of
Yeah, I got you.
donut type of shape.
Yeah, what is with you in the donut, bro? You and McToon are like, are you guys all right?
I don't know. Stephanie said it was a torus field.
I know, but like you're like, but like you just can't say donut regularly. You're like a don't like you're saying something naughty. Like, what's up? You all right?
Sorry, dude.
Yeah,
Donuts are delicious. I love me a donut.
Cool.
I mean, as soon as you got that up, I'll make you big there.
Yeah, I'm just looking for the. Where do I have that? I know exactly what you're looking for. Just can't. I can never find it on the spot.
We could build a map of it. We could build a map of how it rotates.
Oh, here you go. Here, check this out. What do you think of this? This is kind of this is an early conception of it, where it was kind of following the like kind of flowing with the toroidal movement. But I don't know about all that, man.
Okay. Kind of. Yeah, is this? Did you draw?
Loosely.
Okay. Yeah. That's one of my slides, right?
Mm-hmm.
Yeah. Okay. So yeah, that is exactly what I'm talking about, and you can kind of even see there's one in North America and there's one like in Russia, but that they're tilted on each other.
Yeah.
And that tells us that the axis is not just a bicycle wheel; it must be much more complicated than that.
So you're saying right? there would be like different flow rates within like an ether within the ether, so to speak. So like. So the inner donut, I forget what they call that one. What's your inner donut? The hyperboloid or whatever? You know what I'm talking about? What's the word?
Hyperbolic?
Anyway, the little mini donut, right? So like that would have its own ether wind, and then the outward extending one would have its own. That was my early conception of it, but I didn't feel like that was I wasn't on that. I wasn't on board with that one.
Okay. Yes, way more. Okay, I'm going to put Stephanie's comment up on here. Yes, way more complicated than the pizza y'all make fun of. Right on, Stephanie. I don't think it could be as simple as like a pizza or bicycle wheel model is what I'm saying here. If you want to build a model of this, you'd have to say it's complicated, and then you could build it, right? We could build a model that does this. How would the flow be flowing?
Well, it would diverge and converge back at the center, right?
Unrolled. So this is flowing this way. This is flowing in a spiral.
Can you pull yourself? Can you pull yourself up?
You could build that.
So you like this one better than uniform motion? That's crazy.
Well, here's the deal. I like it better than uniform motion because the one you're showing now conforms with the measurements that you yourself highlighted.
Well, hell, then I guess I like it a little better than too.
With what you showed.
Yeah. Well, that's good, man. And I appreciate you pointing that out because I totally had a different perspective on that because this was my original thoughts on it. But I was like, nah, this isn't like my problem with it personally was like I couldn't explain a mechanism for the motion here being different than the motion outside. Why wouldn't they be the same? You know? So I just was like, so I was just honestly, like, well, so I was just like, why isn't it just the same then?
That's my why. When I ask you, okay, there's the what, right? This is our best available diagram of the what is happening. And then if I ask, well, why is that happening? I don't think we have anything like any kind of idea of why this should be the way it is. It's just that's the way it is.
Yeah.
Is that right?
Yeah, sorry.
I mean,
you're good.
The Globers are all out there and they're screaming it into the screen right now and they're saying, right, that's why this is stupid. but to be fair, that's a perfectly reasonable way to approach science, which is to make the observations first and then try to build a model that describes those observations. And then we can start searching for the why behind the model. And that's right. That's the story of how gravity, right? Gravity, everything falls. Okay, fine. And then Newton comes along and he builds a mathematical model of how gravity seems to work, but he has no explanation. And then Einstein comes along with a more advanced mathematical model. And I made you small if you want to.
Yep.
On stop screen. There you go.
Yep.
Yeah, and Einstein comes along and with a more advanced mathematical model with a better explanation behind it. He's kind of got a why finally. And so if we're happy with doing science in that way, then we have to accept this ether vortex torus as following in that same thing. Right?
Respect, bro.
Okay. We would need to see what's going on in the middle. Space Miner, let's just throw it to you, Alan. Space Miner says, it seems pretty important at this point that we would need to see what's going on in the middle.
Dude.
Do you mean by middle, you mean like at the North Pole?
Yeah, he does.
That's the simple part. That's where they match, right? That's where the globe and the torus match.
So they say.
Okay, awesome. So I'm ready to stick a pin in that one and call that done. I think we both have improved our understanding of how this vortex model works and what its purpose is. Did you want to go on to something else?
No, I'm good, man. I appreciate the what's the word I'm looking for? The pushback on it, because I was thinking back on it now. Like, I'll rewatch it obviously and double check, but I'm picking up what you're putting down with that. So I'll definitely have to rethink some stuff on it, man. I appreciate that. This was a great conversation, and honestly, throughout the day, I kind of was like a little I don't know what's the word. We haven't talked in a while, and I was like, man, is this gonna go bad? Like, is this gonna be shitty? Like, So, and I was a little hostile earlier, but anyway, this was a great conversation, and I appreciate that. And for those of you who want to ask these kind of questions and get pushback and find out, like, where the limits are on what you're putting forward, versus what the mainstream says in a constructive way, definitely hit your boy up, man. So thank you for that. I appreciate it.
All right, cool. There was something you wanted to talk about. I've totally blanked on what it was. I think it was measurement arms.
Oh, that was a joke, bro. When you said that, I was just like spit back and forth. That wasn't. We don't have. To, We don't have to touch on.
You weren't serious about that.
No, that was just in jest. Thank you though thank you for taking it seriously. Yeah, I apologize. I should have. Dude, I almost sent you a message to be like, I was just kidding. Like, you don't have to do any research on that or anything. My bad. But I was like, he probably gets it, right? But yeah, my bad.
I don't think I really prepared much for it, but
yeah, it's all good.
Okay. So I guess we're pretty wrapped up. You want to take any kind of questions you're on your chat too, right?
Yeah. Does anyone have any questions I can science that from my chat, or if anyone has any questions for me from his chat, hit me up. We can do a quick 3 or 4 minutes on exchanges. Let me scroll through my chat and see if there's anything going on for you.
Yeah, see if there's anything that's actually like a legit question in here.
Give it a couple seconds. There's a couple.
Or any kind of like constructive comment.
Yeah, what'd you think of the McToon debate? Was it good entertainment? Did he crush it?
Yeah. I mean, it's all right. I think I'm kind of disappointed with that format of debate. At least you guys aren't like, there's a question coming up. We'll get to it in a sec. At least you guys aren't like screaming at each other or anything. which
Yeah.
is really good. That's a huge improvement. But you were both really just reading your notes.
Yeah. See,
And
I agree. That wasn't the best. And so I've been doing like presentations and stuff, and I started off just like, oh, just read the slides and all that, but that's not how you do a presentation, right? You have to know the material and just be able to flow it, right? And I should have done that with the stuff with the debate, but it was like very technical heavy, and I wanted to like say specific things like in a specific order. So I was like, I'll just read it from the thing and it'll be all right. And I totally regret that. That was a if I could go back, I would summarize it way differently, and then jump into the conversation aspect of it way quicker. Totally agree with you on that. But yeah, the format, the way that I kind of conceptualized it, because like the modern day debates and stuff are always like super under, what's the word I'm looking for? Like it's a
under
mismatch.
moderated.
Yeah, under moderated, and there's a mismatch in like knowledge discrepancy, because like maybe one person's like hyper specific on some area of this or that, and like but they don't know, so there's just kind of a free for all, and then you got two people that don't know about each other's subject. So I wanted to not leave wiggle room to be like, well, I don't know, or whatever.
Yeah,
So that's why we
I'd
set
say
it up that way.
you did a really good job of presenting like legit published research, which is pretty unusual. Um, and so you were like the parity between yourself and Tune was pretty good.
Yeah, I thought so. I thought we were pretty evenly matched in that regard.
Yeah, I mean, I told you earlier, one of the points I thought that you made that was one of your strongest was that apparently there were 14 corrections to the atomic clocks
Oh
made.
yeah.
And right, and I was like, yeah, I want to see that. I want to see, because my understanding, of course, is that the atomic clocks are accurate to a second in a billion years or whatever, right? They would not need any kind of corrections.
Yeah. Yeah, that's kind of what they
And
tell
so if
everyone
they
that.
do need corrections, I want to know how big is that correction?
Yeah.
How often does this happen? Why is it? And so forth.
So let me link
So
you. I can link you a couple of papers on atomic clock synchronization, because that's what they tell us all, and we all thought that. We're like, oh, cool, yeah, atomic clocks just go forever in
it's
perpetuity, but that's not the case. So
definitely
so
what we're taught. It's what the science textbooks say.
yeah,
We do have a couple of knowledgeable professors here
yeah.
in the chat. If anybody wants to chime in on atomic clocks, my understanding is that they're obscenely accurate, and Alan is, I think, suggesting that they are not as accurate as we are being told.
Well, it's not
So
that they're not inaccurate. It's that they desync at varying degrees, and that keeping them accurate is
well,
like is kind of like a it's kind of like a trick, using air quotes here. It's not like a trick, but I kind of explained it to you before. If you want a quick rendition, they keep cesium excited at a certain rate so that it oscillates at 12 billion times a second, and they use two counter rotating magnetic fields to keep it, within that parameters. And then anything
yes,
that's outside of that, it just gets kicked out of the field. And then they shoot a microwave at it to, keep it at that oscillation rate when it's losing energy. But it experiences decay at varying rates, and then then there's those random spikes that happen, and that's what Lewis Essen was talking about, like the guy that made the atomic clocks. So like if anyone knows about random spikes and how they work and all that, it would probably be the guy that made it. But yeah, he talks about all that, and then further, when they get into Einstein clock synchronization, there's problems with it, and so the way that they
so
do.
well, hold on. I mean, before we go into the whole like thing,
Mhm.
what I heard you say there was they're amazingly perfect until one of them just sort of jumps.
Well, no, they're constantly jumping like this. These are that like that microwave energy and the magnetic field situation. Like these are
Yeah,
constant corrections to keep this going. Like it's not like it
right.
just does it in
So
perpetuity. And
yeah,
then
but they can't like fudge it using that. They can only hold it at a steady rate, right?
no, I'm not saying that that's where that's where the problem is. So the way that they make these corrections, like I was going to show you this paper by Paul Marmot, where he shows the equations that they use for the corrections. It's basically the way he breaks down. It's just the Sagnac effect. Like they're just correcting for the like the first order movement of the velocity of the craft, whatever it is. So that's all they're doing
Okay.
to do
Well,
the corrections.
I agree with that in modern understanding that the clocks need to be held in sync. They need to be corrected for various relativity situations.
Sagneck effect's not a relativistic effect. None of
Yes, it
the.
is.
Oh yeah.
Well, I mean, I'm sorry. I should say it's taught that way.
Yeah. It's taught to you that
You don't agree with relativity, so of course you're not going to agree to that. But
should an inertial observer see a variance and see?
I'm sorry. Let's come back to it. Let's answer Space Miner's question, and then let's come back to that. Is there a correlation between moon and field models? I don't know. I don't think so.
Couldn't tell you.
I don't think there's no correlation between how the moon acts and the toroid of ether, right?
Not that I'm aware of.
Did you have anything else to say about that one?
Not that I'm aware of.
Okay. All right. So back to you then. You were saying the Sagnac effect, and you had a question about it.
Yeah. Should an inertial observer see a variance and see?
No.
Okay.
Special relativity says that an inertial observer measures C in a vacuum, C, always the same. That's what SR is supposed to say. Yeah.
Is a device in uniform rotation not an inertial observer according to special relativity?
It is not inertial. Rotation is not inertial.
Have you seen Einstein's thoughts on the matter?
Yes.
Okay. Why do you differ?
He was very clear.
Why do you okay.
You can run this. This is done in probably freshman physics. I mean, freshman college level. It's in undergrad college level. We do this in modern physics. You take the course, you do this. If you simply measure the distance traveled around clockwise, measure the distance traveled around counterclockwise, divide by C, Sagnac effect. It's simple as that. The inertial observer, the outside person who is not rotating, can do this, and it's straight up.
Yeah. So Einstein says that if you're not, or if you're in uniform rotation, then you're an inertial observer. His equations hold true in that regard. So, so if the device is rotating uniformly, then it's an inertial observer.
So
Special
the
relativity
Sagnac thing, the inertial observer is the person outside the rotation, and
okay.
When you watch, you watch the rotation.
Gotcha.
And that person is then inertial. The observer is inertial, and therefore you don't have to do any of the fancy stuff.
Sure.
You can just run regular C equals distance divided by time.
Okay. Well, let's try. So you're saying that so first of all, the observer, where the photographic recorder is, determines where the observer is. So an observer watching the experiment would not be the observer on the rotating the device. The observer on the rotating device that's rotating uniformly would be the observer.
Let me clarify. I'm saying that in order to simplify the mathematics so that there is no question of how to do this, according to relativity, if you are rotating, the mathematics are complicated, and we don't want to do that in undergrad physics. But if we simply place an inertial observer outside the rotation, we can work the math from the perspective of that person.
Oh, okay.
That result must be shared. That result must be the same
in all frames
as all frames.
Cool. All right. Can you put me up on big screen? Let me show you this real quick. You're gonna love this. This is crazy.
Okay, go up on big
this blew my
screen.
mind. This blew my mind, man. So check this out. Okay. This is your boy Dufour and Pruner, two Frenchmen in 1942. What they did here is they reproduced the Sagnac effect of 1913. Nothing too crazy there, right? So, no violations of special relativity as according to the textbooks, as just stated. So here's the configuration of their device. Now they make the argument, and there's other experimental evidence for this as well, but let's just go with what you said, that the photographic plate here, it doesn't determine that it's an inertial observer. You have to be off the photographic plate to determine the inertiality of the frame. Yes or no?
You have to be off the photographic plate.
I'm sorry. You have to be off the rotating device to be an inertial observer, right?
To
Because
be
the
truly
device,
inertial, correct.
correct. Okay, cool. All right. So they did a couple configurations of this experiment where this is the second configuration, where they took the source of light and they put it on the lab wall, fixed frame, station, an actual inertial source, right? And then they have a collimator here and a collimator here attached to the rotating device. Just refocuses the light beam so that it can complete its circuit. And then it hits your boy photographic recorder right here. But as we were talking earlier, this is a non-inertial frame according to the textbooks and whatnot, and according to making the mathematics easy. Yes. Okay.
Sure.
And this produced the same effects as the Sagnac effect in the traditional configuration. So still
It should.
yep.
That's
So
what SR says.
yep. So still in alignment with special relativity.
Okay.
And then here's the fringe patterns for this for the comparison. So it's exact identical. And then they get into this really interesting configuration here. And this is where they have a stationary light source here. They have a photographic recorder here as well. And then they got their collimator here to refocus the beam. And then they got a stationary platform right here, right? If you can kind of see my hands. So stationary platform here with mirrors angled at 45 degrees. The light comes in, hits the bottom 45 angled mirrors, and that's on the rotating platform. So the devices, so the path of light is going to go from the stationary lab frame, hit your boy's stationary beam splitter, deflect off of these mirrors, complete its circuit, go back, and then here at R, there is a photographic recorder placed as well. So it's going to take a measurement here for an observer on the rotating device, and it's going to take one for the stationary observer on the lab frame. Make sense so far?
Yeah.
Okay. And these devices are not connected. They're separated by 4 inches of nothingness. So the rotating device is completely independent from the stationary device. And then let's see. So this is the original conception of the configuration. They had to make a couple modifications or whatever, but this is the end result. Same exact configuration, lab frame, blah, 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 right? And then you got C here, which is just the central axis of both platforms that it's rotating. Here's a quick snapshot of what it looks like. So they're separated by 4 inches. The top platform, stationary, non-rotating. Bottom platform, rotating at 1 turn per second. And what they showed here is that the fringe shift for the lab observer shows a first order dependence on the 1 turn per second of the rotating platform. And also the
Are you telling me that they took different pictures?
What's that?
That they're looking at the same target and see different things?
No. The inertial observer on the wall, right, sees a fringe pattern based on the rotation of the rotating platform that it's not connected to in any way.
I don't see that there.
Yeah.
Is that 146 or 142?
142.
142, I see no fringe shift.
Yes, there is a fringe. And then
there is?
Yes. And it's identical to the one that's on the rotating device. And then they get into it's crazy, dog. And then
I don't see that. In the picture you just showed, I would not confirm that.
Okay. Well, they've got their data, and then like Paul Levoux, anyway, we'll get into it. So this is what they showed with their observations. This is what they got. And they go over what
is the upshot you're going to tell me?
Yeah, so they go over the relativity prediction. So as you were saying, with the convenience of the frame, for the mathematics sake, right? Paul Levoux chooses the central location, or like the center of the rotating platform. I'm sorry. Let me rephrase. So for special relativity to derive the effect, it chooses the location of the rotating platform and it derives the effect. Cool, no problems, right? But if you put the if you calculate the distance from the traditional Sagnac configuration, so instead of being where it would normally be, it would be at the location of the photographic recorder on the device. So if you do the fringes from there, the classic theory predicts a fringe of 0.053 in the fringes, and relativity predicts 0.005. Like it's not able to show to make the prediction. Like, so in the way that you were saying, well, they just choose it out of convenience because the math's too complicated. Well, it didn't give the prediction unless it uses that preferred frame. Like it violates Lorentz symmetry in that regard, and it shows that the speed of light varies for an inertial observer. And then all Paul Lavue had to say on that regard, and I don't know if you know who Paul Lavue is, but we can touch on that in a second. But all he had to say about the matter was, well, if the device is rotating, we have to choose the center of rotation, and that's all I have to say about it. And then he dipped. So he had nothing to say to counteract that.
So your upshot here, if I'm hearing you, is that according to this guy, changing from an inertial to a non-inertial observer changes the observation.
Well, no. The inertial observer. See,
we don't have time to go through an entire paper here.
Oh, okay.
What I said was about the SAGNAC was you can arbitrarily locate your observer anywhere, work the math.
No,
and
you can't
take a picture of the fringes from any observer. They should all see the same fringes.
Yeah. And if they don't, though,
you're saying that they don't.
Yeah. They see a variance with a first order dependence on the rotation of the platform.
That would be really interesting. I'm not aware of that, although it seems like perhaps it could be possible. I know that
I'll tell you what.
SR claims, or GR even claims that if you're accelerating, then time varies and therefore events look different, but doesn't seem like you could take a picture of outcomes that are different in different reference frames. And if any of you guys online knows better, tell me if that's so. Seems like there's a paper from 42 that said that.
Yeah, it was done by DeFore and Pruner, 1942. And then also, like I was saying earlier, Paul Lavue was made aware of this experiment, and he flew in to talk to these guys about it. You can read the whole thing. It's very interesting. And his answer to it was basically to just kind of say, well, we have to choose the center because it's rotating, and then that's it. But the observer is inertial, man. So like I don't know. That's interesting. Check it out. Let me know what you think. Because it's a new one. It's a new one, man. Like I know a lot of people, it's a new interferometry thing. So check it out.
I'd probably go out on a limb and say this is, it's an aberration. People have done all kinds of experiments over the years, and
do aberrations produce first order effects though, or no?
I'm pretty in the box with my perspective on it. So
yeah, that's cool.
I tend to think that we get aberrations from time to time, and then the ones that can't be reproduced or are explained in some other way, we move on and we don't go back to them. That's not what we teach in class. We teach the ones that work consistently. But I guess your whole perspective is that hasn't happened in this case.
Well, it just shows that the speed of light is not the same for an inertial observer as it would have to be, as claimed by Einstein.
Okay. Yeah, we should do that next time. It's 9 o'clock and we could wrap up, but yeah, that was definitely something MC Toon wanted to get to.
Dude, he wanted to get to it by saying that he disagreed with it, even though like the math and the all that facilitates the first order effect. It's not really anyway.
Well, no, he has an interesting point about like all the various interferometry experiments and whether they show a difference. And I think you like to point out that they do show a difference.
Yeah.
Whereas we are taught that they don't, right?
Yeah. Well, isn't it weird though that you could just like look up and see that they do, and then like that's weird that they teach you that they don't.
I don't see that they do.
They do. They specifically
see noise.
They say that. I got you. Okay, word.
Right, and we look at the paper together. We both see noise, right? Let's not mince words. They are noisy as all hell.
Okay.
And so what Miller did in particular.
You still got me on the big screen if you want to put me on the little one. No, that's not what he did at all. But that's cool though that you think that.
That's absolutely what he did. He got noise.
Is that what Marisa Elias did when he analyzed it too? And then James Demio? Were they just analyzing his repetition of noise?
Yeah.
that shows a
Well, I mean,
that shows a
you know what I mean by
fluctuation matched
noise,
with
though.
sidereal time? Like, I
That's
don't.
not supposed to be. That's not supposed to be a controversial statement. Do you not agree that it was noisy?
The way that I was interpreting what you were saying is that it was a nothing effect, and that he extrapolated
It was
nothing.
it noisy means the oh, you're on full.
Yeah, yeah.
um,
There we go.
noisy means like here's a not noisy signal, right? Not noisy. Here's a
Mm-hmm.
noisy signal,
Mm-hmm.
right? Um, Miller's is noisy. It jiggles all around, right?
It jiggles.
It's not a smooth curve. It is very bouncy,
What?
right? And so that leaves a lot of room, a lot of wiggle room for the two of us to interpret it differently. Like I could say it's too noisy to interpret that as the pure signal inside meaning anything. And you could say that when we smooth out the noise, the signal is underneath there. And I think that's why people can both look at the same paper and interpret it differently.
Yeah, man.
Okay. But there was something MC Toon wanted to say, and I think it's a good point, and that is Miller came up with a direction and magnitude for the ether wind.
Mm-hmm. Of an Earth moving at a velocity of 1,000 miles per hour, roughly.
Okay.
So, you know,
I don't remember. I have it here, but I don't remember what it was. Do you agree with that?
No, the Earth isn't moving. He extrapolated the direction based on the effects that he was measuring. He mapped out the axis of rotation of it, so to speak, which actually, dude, I think you might be okay. Yeah.
So wait.
Mm-hmm. He mapped out the cosmic microwave background, basically. But go on.
So Miller showed that there is a variation in the speed of light in different directions. Yes or no?
Yes.
And that is because of ether flow, ether wind. Yes or no?
Corresponding to the movement of the sun. Yep.
And that's not what Miller said. Miller said that it is pointing from a particular direction with a particular speed. Correct?
The fringes reach their minimum and maximum dimensions on the equinoxes. That's what I'm referring to. You're referring to the direction that you're referring to the directionality that he extrapolated out of that to assume that what he was measuring was motion of the Earth and not the motion of the sky. But continue.
Right. It was not constant. It was not a constant that Miller measured. You're saying the speed that Miller got varied throughout the year, right?
Mm-hmm.
Okay. And the direction also varied throughout the year. Is that right?
No. What do you mean?
No, just the speed. I'm not sure.
Yeah, I don't know.
I didn't read that follow-up paper. Miller only gave one direction and speed, but the next person you quote reanalyzed Miller's work.
Yeah. So when they do the reanalyzation, like you got to remember, all these guys are going to interpret it as the Earth moving through something, right? But I'm interpreting it as a station. We don't have to go
there, right? We can totally say that it's the ether moving past the Earth.
Yeah, that's what I'm saying.
That's fine. I'm fine with that.
Yeah, well, I mean, that's what you're bringing up.
The direction and magnitude. Do you agree with it or not?
I agree with so let me pull up the model and show you what he mapped out. And I agree with this in the respect that if you map it to the sun's ecliptic is in alignment with the cosmic microwave background. I absolutely think that he mapped out the cosmic microwave background, because this blew me away when let me pull up this model real quick. I was like, what the hell? It's awesome. So ether, 1 second, pull this up. James 1 second. It'll be in the pictures here. Yeah, right here. So yeah, this is what he thought he was measuring based on the axial tilt of the Earth and whatnot. But if we live on a stationary plane, then everything would just default to the sun's ecliptic. So it would be relative to that.
Well, hold on.
Mm-hmm.
We're going to bump into this again.
Mm-hmm.
It seems to me that if we live on a plane, there is no ecliptic. It's not a plane anymore. We've had to twist.
No, the sun's movement.
The plane of the ecliptic is now Pringle.
No. No, the anal limit and all that would still be the same on the
The,
flat Earth. It's just the
the
movement
plane of the ecliptic is the plane that all the planets move in, right?
of the sun. Sorry, all with respect to the sun. So it would just default to that. That's how it is in geocentrism and a neo-Tychonic model. It would literally be the same. So
Right, but geocentrism and neo-Tychonic, whatever, are both globe models. They're not flat models.
it's just mapping it to the sun and removing an axial tilt and putting
Well,
it
but
on the
if you do
sun.
that, right, if you unwrap the globe, just like what we saw with the ether vortex, if you unwrap the globe,
Mm-hmm.
things that were planes become twisted.
Well, luckily the sky and solar system above us is already a plane, so we're good to go, brother.
I'm sorry, what?
What's that?
What? Where that's a
They
it's a
all they all
plane
they
now?
all orbit on the same plane. All the planets and stuff, right?
Okay, but the planetary motion
Mm.
on a flat Earth is not planar anymore, or is it? Is it? I guess planets don't move in 3D, right? Planets just move in 2D on that plane,
Yeah, I think so.
and the sun moves around on that same plane, right? It
Mm.
moves in a circle, almost a circle, in that same plane. But the
Yeah,
planets do some weird stuff on that plane.
yeah. Let me show
So when,
you.
so when you say plane of the ecliptic,
Pull up a video.
that's what you mean? The plane
The
of
sun's the sun's ecliptic.
the sun's ecliptic.
Yeah, let me show you this. So we got two things here. Let me see. Let's see. So you got your boy cosmic microwave background / movement of the sun, right? So over a flat Earth, that's how it's maintaining its altitude for everyone to see it in the northern hemis. That's what it's producing. Do you see that? Then I'll show you one more slide.
Yeah.
Okay.
Here's an example of a quote flat Earth debunk.
1 second. Oop, that's not the right one. Nope. 1 second. Sun movement. I'll have to come back to it. Give me a second. You can.
Well,
Talk,
I don't think we need to go into this much depth in order to answer the question that MC Toon is bringing up here, that I wanted answered, which is the direction of the ether flow and the speed of the ether flow. Do you accept Miller's results of that?
No, the flow goes east to west.
Okay. All right. That is the key. That's the key question. And I'm going to say now, you accept Miller's findings that there is a flow, but you reject Miller's findings of the direction and speed of that flow.
Yes, he's mapping it to a globe. He's assuming that he's actually tilted and all that.
No, the globe or flat. All he gives is a direction into the sky and a speed.
Did you
That
not?
has nothing to do with whether it's globe or flat.
Did you not see his model? It's literally all based on the axial tilt of the
Well,
Earth
look,
and the Sun, based off of his data on the equinox, because it matches
That's
sidereal
fine.
rotation.
That's fine, but unroll it, right? Unroll it onto your flat model.
I did.
And just take his direction and his speed, and it had nothing to do, his results had nothing to do with the plane of the ecliptic.
No,
They were outside the plane of the ecliptic.
so if the Earth were moving at 30 kilometers a second, they would have measured that in full.
And he measured instead what?
So he measured like just a little over one fringe, and they interpret that as 5 kilometers a second. So Miller being just over it, like slightly over Michelson and Morley's, they say that that's 8 kilometers a second. Now, that's tied to how they were trying to interpret it through the orbital velocity. When you just plot it to sidereal time, it matches within 98%, shows the fluctuations when you plot circular interferometry, so like a Michelson-Gale or whatever, right? It shows a 98% match to sidereal time. When you plot Miller's linear interferometry data against sidereal time, it shows a fluctuation corresponding to the equinoxes. And we know that there's a first order dependence on the rotation of a device, and with Ruyang Wang linearizing the Sagnac effect, we know that full linear motion would be detected. So if the Earth were moving in that direction as he thought it was, he would have got a much stronger fringe. So that's why I disagree with all of that.
That isn't what I asked about at all.
Well, that's why I disagree though, because if you're trying to get me to like agree to it, I'm explaining why.
Can we answer what I asked about?
Yes, I don't disagree with it because if the Earth were truly moving in that direction, the readings would be much
It
stronger.
doesn't matter if the Earth is moving or it's the ether moving. Okay, can we just say that? Let's not even talk about whether the Earth is moving or not. Just set it aside.
Yeah.
Okay, we should, if there is an ether wind, we should be able to measure the direction that wind is coming from and the speed of the wind.
Yes. So
And Miller did that.
it's the speed of light is faster going east to west. That's
Okay, but that is not what Miller found. Miller found that the speed of light is faster coming from a point in the sky, not from east.
based on how he thought the Earth was moving when it's not.
Are you telling me now? Are you telling me that the direction he measured, he rotated it up into the sky for some reason?
No, the variance is shown in other forms of interferometry and in GPS, where it shows that the preferred direction is east to west. When you look at Michelson-Gale-Pearson and that experiment,
Okay,
the variance comes from east to west. The variance comes from east to west.
Okay, but Miller did not find that.
Don't give a shit what Miller found, bro.
Okay, then, then I'm going to throw it back on you. Then we're not going to give a shit about what Miller's found.
In regards to the Earth motion, yes.
You don't cherry pick which results you liked and throw out the ones you didn't.
I'm not
from the same data set.
I'm not in the full context of interferometry. Hold on a second. Hold on. As in the full context that I explained to you, that interferometry would register the full amount if the Earth were in motion at that speed. It does not. That's it. So when Miller extrapolates that the direction of this and that based on all that doesn't mean anything. When it was reanalyzed, some guy found a different direction. Doesn't matter. You trying to tie me to that is making me disinterested in the conversation. I'm getting super bored with it. We need to either move on or talk about something else. Because I've explained to you multiple times now that there's a first order dependence.
But I think you're highlighting a real problem there. That if we can't talk about something because it stings, then that's a serious bias.
It doesn't sting. I've answered it adequately, and you keep repeating it.
You have not. You have told me. Let me echo back what I understood. What I understood was Miller found the speed of light varies in different directions. And the direction that Miller found was wrong.
Based on him assuming that the Earth is moving and rotating.
Miller didn't find it. Miller's data is crap.
Not all of it.
Not all of it. Okay. All right. I think we better move on because you seem upset about that one.
I'm not upset. I'm frustrated that you keep repeating the same thing and you don't acknowledge that there's a distinction between measuring the full effect of motion and not. That's why I deny, or that's why I don't accept his interpretation of it.
Frankly, I don't understand measuring the full effect of motion and not. Please explain.
Okay.
Without going on to these other things, just in the context of a Miller experiment, what did they fail to measure?
Just in the context of the Miller experiment, you wouldn't fucking know, and you would have to agree with Miller. That's why the full context shows that the motion that you need for the Earth to be moving doesn't exist. That's why I don't take Miller's reading as a direction of motion for the Earth. He assumes two different vectors of motion.
Okay.
For his interpretation.
Trying to be as objective as I can be.
Why don't we object to something else then and just move on?
Okay, we can just move on to something else. Did you have anything you wanted to ask me?
No, I'm good.
Okay. Yeah, that was really my other thing that I think I wanted to ask you about. Well, do you remember what the other thing I wanted to ask about? The single axis. Yeah, I wanted you to explain to me why you want a single axis interferometer. No, not interferometer. Single axis gyro. Because I kept saying like a 3-axis gyro is 3 single axis gyros.
Yeah. So
explain that.
Yeah. So in in the context of the debate, and not just the debate, but just overall, these correction angles are like, globe, or, quote unquote, globe proof, right? So to say that as if there's like rereadings all over the place and there's more data to like substantiate that claim and back it up, I was looking for that data, didn't find it. So like that's where the pushback was from that. So to supplement the lack of single axis readings, Toon said, well, we have inertial navigation systems which have multiple axes or multiple gyros per axis, blah, blah, blah. They do the readings. And then my contention to that was that this is it's a computer system that takes readings, has a data set that it compares it to, does all that, sends you an output. So like, so in terms,
you keep referring to the Kalman data set, and I have no idea what that is. Could you please show?
Yeah.
What is the Kalman data set in context of an inertial navigation system?
Gotcha.
Yeah, that was what we were going to do.
Yep. So in the context of an inertial navigation system, we'll give a quick rundown of what it is and why my contention of accepting the output readings as proof to supplement a single axis gyro.
Straight to the Kalman thing.
Yeah, sure. So the Kalman data set here, where is Kalman? Let's see, 1 second. Okay, the philosophy of the Kalman filter. So what this does, this whole data set here, what it's doing is when the device is calibrating, it's taking its readings and then it's like comparing and contrasting to the quote unquote known readings or whatever, right? And that's what it's doing. It's just narrowing, zeroing out like the noise, so to speak. Because what they do also is to prevent what they call frequency locking. I'm not sure if you're familiar with what that is. They vibrate the device to induce a fringe pattern, and then they zero that out. And part of all of that zeroing out and comparison and all that is facilitated by this Kalman filter, the Kalman data set that's in the inertial navigation system.
So it's a Kalman filter. Let's go back to the Kalman filter. The Kalman filter is essentially a low pass filter. Am I correct?
What is a low pass filter? What is that terminology?
A filter designed to smooth out the noise.
On the surface level, that's what it says it's doing. Yes.
Okay, so as far as a data set, there's no data set with that other than just the parameters of the filter, right?
No, it's taking the readings and comparing it to the Kalman data set. So there's a data set that accompanies this.
Show me that.
Show me that,
because that's not what that line there said. The highlight you first showed said it was a filter.
Let me see. Kalman data set. Kalman filter.
Clive is asking, a single axis will only respond to the relevant component of the angular velocity. Not sure why you would want that. And I think that would be very useful in that you could then tilt it around until you found the local maximum, which would then be the axis, right? You could find the axis of rotation with it. And I think that's the reason we would want one. Okay, and you're looking for Kalman data set.
Yeah, can't find it.
Yeah, I got a hint for you.
Can't find the terminology. Go ahead.
The hint is reread the Kalman filter. You're thinking of the Kalman filter, and I think you've misunderstood or conflated that with some kind of lookup table. The Kalman filter is a smoothing function to eliminate vibration.
Oh, okay. Yeah, we'll definitely reread that and take a look at it then. My understanding of it was that it was comparing the data sets relative to the latitude to make sure that it was getting the readings, at where it was at when it was doing its calibration.
No, because like this is just a gyro, right?
No, it's a computer system. Here's the schematics for it. It's a whole
right, but the workhorse of it are gyros and accelerometers, right?
Mm-hmm.
And so we use it to measure when the aircraft or whatever rotates. And that doesn't correlate with any particular latitude or anything. That's just how we get where your nose is pointing and stuff like that.
Yeah, so then the way that McToon was even trying to apply the inertial navigation system wouldn't even make sense then. So.
Well, I don't know. How was he trying to apply it?
to supplement it for single axis gyro corrections, as if that
Well,
was, as if
it's
that.
got 3 of them in there. Well, it's probably got more than 3, right? Because it's got redundant ones.
Mhm.
But they'll tell you the orientation and how the orientation changes over time. That's what it does.
Well, after you've booted it up, told it where you're at, entered your coordinates and all that through, maps and or GPS locations, and it's calibrated, then it's going to, it would produce whatever it would needed to as you move through the coordinate system. So, like for example, here they have a special mode when it hits the 45th latitude or 65th south latitude, it switches to polar navigation mode, where it uses an entirely different coordinate system set. So my contention was that if you were to take this device at the equator, for example, it would produce an output reading that would, supplement the single axis gyro corrections. It wouldn't contradict it, but you wouldn't know that it was being corrected on the back end because the coordinate system just switched to give you the relevant output. So that was my contention to it. And
Okay.
yeah, go ahead.
So if I could say that back, then it's a complicated, and a full INS is a complicated, interconnected, programmed thing, and it does not give you the raw data of just what each gyro is saying. Is that fair?
Yeah.
Yeah, I've even asked Wolfie whether maybe somebody on the ground crew can extract the single axis raw data, but I don't think we can. I don't think anybody can get that.
I've heard that it's classified to break to do that to those systems.
It's just not designed for that.
Yeah, and or that that it, like for the planes, for example, like they're not allowed to do maintenance on it. They have to take it back to the manufacturers if it has any problems with it.
Right, so we don't crack those things open.
Yeah. So in terms of like finding out, his point was like these single axis gyro readings, where you would have the raw data and all that stuff to confirm it would be that. So like that was my argument against it. Yeah.
Clive is saying classified, but no, it's not classified, but they are sealed units. I think we can agree to that. I think they're sealed up units. You don't open them. End consumers are not expected to repair or whatever those things. But if you get the cheapest you can get is a single axis gyro. You can get a 3-axis gyro also from the same companies, and they'll make you can get raw data from those. I think, does anyone remember whether Bob's was a 3-axis or a single axis?
It was a multi-axis. He had a $20,000 INS. Like, yeah, it had to have been. There's no way it was a 20,000 without 3, right? Like that'd be crazy.
I don't know. It may not have been 20,000. He didn't pay for it. He didn't know how much it was.
Yeah.
And I guess I wanted to bring us back to that. And that's something we've talked about before. I priced it out a little bit, and I looked on like eBay. You can get a used single axis gyro. You can get them for probably cost you about $1,000, I think.
Yeah.
By the time you got one, and stuff. So if we got one, right? If we did a little fundraiser and we bought one and we put it together, and then we did various experiments with it.
Dude, that'd be dope, man. That'd be dope.
I think it would be pretty awesome. It'd be a lot of fun. And then we would have to invest some more money, I think, because one of the things you said was you want to see the results south of the equator.
Yeah, I would like to see on the equator and south, because from my understanding.
So what we could do is we could ship it to somebody down south, or we could, fly around the world, fly around the globe, have just an awesome time flying around.
Alleged globe.
Taking measurements. So yeah, maybe we should start our fundraiser to fly around the globe and take measurements. But here's what, and the people have offered to even fund it. Right, there are people with enough money that they would just plain fund it.
Mm-hmm.
And I told them no. I told them let's don't. And here's why: it's not going to change anyone's mind. And I want to say this again. Would it change your mind? Would you care? What if we get 15 degrees per hour aligned just like my diagram?
Before I had the understanding of interferometry that I do now, I wouldn't have cared because I wouldn't have like understood it enough to give a shit. But I think it would be super significant and like, you know, cool. Like, yeah, I would be totally into it. Like, it would it make me think that the Earth's a globe or whatever because of the readings? And like no, obviously not. But would I value the experiment? Would it be cool for you guys to do it? Would it provide mechanisms to back up a lot of claims that have been going on? Like, yeah, that'd be fucking dope, man. Like, I'm not gonna hate on you guys if the readings don't go my way. But like, is it gonna?
Dope. Yeah. I think it would be cool. It would be dope. I don't think, like you just said, I don't think anyone who's a flat earther would change their position at all. I think even you would change it from what I essentially understand is I'm not really sure what's going to happen past the southern hemisphere to, yeah, it works like that. But that's, I mean, we already got a twisting toroid vortex field. So why can't a twisting torus field?
Dude, it would be cool to have those readings to figure it out though, right? To see the geometry of it. Because you could kind of extrapolate it that either way. Because right now it's just kind of abstract math based on specific locations in the northern hemisphere.
Well,
if you don't accept the inertial navigation readings, right? So
yeah, I mean, it's not like the fact that you can't find them doesn't mean they don't exist.
True. That's absolutely true. And if anyone finds them, please send them my way. My email address is AlanSpaceAudits@gmail.com. Highly interested in those readings if you find them. That's not sarcasm or like it was in the debate. I was kind of being a little, I don't know if you saw that. I was kind of joking around a little bit, but if you do have them, send them my way. I would totally like, I then wouldn't continue to claim that they don't exist. So.
Yeah, I definitely think that they do exist. And yeah, and, you know,
yeah, we'll see. I mean,
they do. We know how this stuff works.
Allegedly,
and there's like, you know, it's not the only piece of data that aligns with that, right? And you accept all the rest of it. So I don't know if you accept all the rest of it, but you accept you know, everything rotates around Polaris, and you understand we have to point at Polaris, and right. That's what that is. That's the same thing, right? Those diagrams that we made are all based on that. So what happens when you go past the equator and you're still trying to point at Polaris? Well, you just keep rotating at the same rate that you've been rotating.
Yeah, so, hypothetically. All right, man. I'm gonna head off here. It was a great show, bro. Thanks for chatting it up with me. Appreciate it. And you know, we'll reconvene at another time, man. Do it again.
All right. Thanks for coming by. Yeah, there's some nasty things in the chat here and there.
I don't care, bro.
That wasn't there.
It's the internet, dog. You gotta have thick skin. That ain't shit.
And I want to repeat for anyone who missed it that we came up with a model of how the ether must rotate over a flat Earth. And it's a little complicated, but it should work. Right?
Yes, sir.
Okay. All right. I guess that's it. So good night, and I'll see you all next time.
All right. Peace, bro.
Bye.
All right, boys.
But if you're in the South, you're assuming that there's a fake celestial sphere and Polaris is beneath your feet. Are you aligning your axial gyroscope to your beneath your feet? No, of course not. There's only one axial source of rotation.
Yo.
Yeah, I agree with
Yo, you crushed it.
Thanks, that was awesome, dude.
Sound bites today are more capable than ever. Their modern geometry and components have catapulted.
Whoa, that is loud.
Yeah,
You're definitely home alone.
That was so
You're definitely home alone, JT. Your wife is not in the building, dude.
Dude, I don't know why that started playing.
Well, that guy was annoying.
Yeah, no, he was. Dude, I hate it. It's a very punchable face.
That's right, Shane. The fucking East dude. I totally.
Yeah,
I totally forgot.
In here, I was like, oh, I don't know if he's gonna see this.
Yeah, no, that's the actual answer. I totally forgot about that. The deprogramming of that. Yeah,
You should
see,
DM it to him right now.
absolutely. I'll talk to him about it later. We just had a lengthy discussion. It's time for us to cool down.
Yeah, you up there?
Yeah. Well, like,
That was good.
like I
Keep it in
said,
the chat.
well, like I said, he's cool and all, and then, but like sometimes we get to like a point where we're just kind of circulating, and then like that's where it gets tension starts building up because I can't, I don't deal with that well. Like I start, that's my
Yeah.
weakness. I'm like, I start losing patience. My ADD kicks in. I'm like, we're just repeating
I don't fucking
ourselves.
care what you said. Let's move on.
Yeah, exactly. And then you have to like, then you have to stomach the, well, you're clearly getting upset, so we're gonna move on. And it's like, okay, dude.
Yeah,
Yeah,
well,
that
that's
was-
what I saw happening, and that's when I was like,
That was lame.
I kept explaining it here to these lads. I was like, okay, what I think Alan is forgetting is that when we first discovered this, he was like, oh no, it goes east to west, and I'm like, no, it's just an inverse interpretive framework. The only possible way to interpret this motion that they're measuring is either a moving Earth and a stationary ether, or a stationary ether and a moving Earth. And they just did an inverse proportional framework. They're saying that because it's moving, the Earth must be moving west to east because the sky moves east to west, right?
Yeah.
And that's just the last step.
Yep. Yeah,
So-
that's funny, dude. Because, oh, sorry.
Oh, go ahead.
I was gonna say that's funny because James Demio, who reanalyzed Miller's work, got their reading in the opposite direction. So he literally
Well,
literally
well, yeah,
corrected
so
what he literally corrected
like,
Miller's
so
mistake.
when he was saying, do you agree with Miller's findings? I would say I agree with the magnitude and not the direction. Like, I would say
Yeah.
the inverse direction and whatever he measured it, because the magnitude's always the same and it's 5,200,000. Like, I wouldn't throw out any of those. I would just inverse the interpretive direction of his results in every single one. And I think that would be fine.
Yeah. Thank you. I agree.
But now he's gonna think he got you because he was like, "Oh, I made him uncomfortable." And
Oh, I don't care. I don't care.
Well, if you said he
So-
was doing it for pride,
So how
so if
did
he's
it?
doing it for pride, then he's gonna.
I mean,
Now I got you forever.
yo, it's whatever though. I got we got so the original ether vortex model with the toroid shape turned out to be the good one, dude.
Yeah, dude, I know. But you also know, like, with that, if you kept playing the video you had up, the third part of that was fucking Flat Earth Philosophy's double donut thing. And if you had seen that, you would have seen it click, I think, because that was what we based the shape on. And that's what I overlaid on that original drawing that you had brought up with those, like, parallel, non-parallel divergent vectors pointing at a middle point in the middle. And Flat Earth Philosophy's, like, double half donut would fit into that, like, perfectly.
Oh, dude, where is that GIF? Hold on.
Right? Like, yeah, I thought you had it. I think the one you were playing had that as like the final animation, but you never let it get past half. You just played it and paused it, and I was like, play it, play it, let it play it. No, play it.
Oh, dude, it goes into the toroid at the end.
Yes, it does. Yes.
Wait,
I remember that.
Wait, where's the toroid one? There is this one, right? Hold on.
Couldn't find it. I was looking for it on the fly.
Is this it right
I was
here?
like, I can't find it. No.
There was
there's
this.
It's a GIF thing. Like, it started the same way as that one, but it ended up with Flat Earth Philosophy's double donut. Like,
Oh, wait,
pie or
wait.
something.
This might be it. Hold on. Nah. I kind of know what you're talking about, but yeah.
Oh, that wasn't it then.
Damn, so the old double vortex. So the flow then would just follow the toroidal field.
Yeah. But like, so the way that toroidal fields work is it has the two halves. Like Flat Earth Philosophy is like, so it does bend in and out, and they would be laterally pointed at 45 degrees to a convergent point. The main takeaway is that the measurements are like latitude dependent. When they say that, it's like, oh, well, they're aligning it to the axial rotation. Technically, he's right with the nitpicky thing he said about axial. It is a point. That's why we say Polaris.
Yeah, see, so that's another thing. I was confused about the orientation. I didn't realize that it was still being orientated or like on the other side of the globe. I didn't visualize it that way. I was conceptualizing it the same as being this way. You know what I'm saying?
Which way? Oh, your camera's tiny.
Oh, shit.
You're a tiny corner of the tiny corner for me.
Like that?
There you go.
Yeah.
Yeah.
So like how
Yeah,
it
like
would be
that.
parallel on the globe. Like I didn't put that together until halfway through, and I was like, oh shit, he's right. So you know.
Yeah, I mean, he made that little point that they would be parallel, meaning like they'd be actually aligned. But that's also assuming that, let's say, Polaris is the infinite distance around everyone, and then like you just move it into perpetuity, and then the angles match up. And they say, oh, look, the vector points at the same celestial object at infinite distance, and the cylindrical transformation, all that shit.
Yeah.
Proud of you, bro. I'm gonna go to bed. I hung in there for you.
Thanks, bro.
Yeah, I was tired of shit. I was like, I want to punch this guy, but Dave's like, we have to watch for Alan. I was like, all right, Dave.
Dude, respect. Thanks for showing out. I'm gonna go ahead and end this stream here. Thanks for showing up to the YouTube chat and hanging out. Hope you guys enjoyed. Sorry I wasn't able to read chat much. I'm not really good at keeping an eye on chat and having a conversation at the same time. I get distracted very easily, and multitasking can be a problem. So let's catch you guys on the next one. I think I'm doing something in the next couple of days, so maybe you'll see me live then. Peace.